All right, in this podcast, we're going to talk about pH indicators. All right, so basically, an indicator is a substance that changes color as the pH of a solution changes. Most indicators are going to be organic molecules that are weak acids, so they're actually acids themselves, and they're colored in solution, or they become colored when they're in contact with excess H plus ions. All right, so like down here is an example of one. Okay, so, all right, if you will notice, this little region right here, we've got an H on there. And this is an acidic solution. And then where there's bunches of H pluses, right? And then in basic solution, hopefully you'll notice that that H is gone. Okay, so there is no H there. All right, so we can write a generic equation for an indicator in solution. So HIN is the simplistic form of the indicator. And when we put it in water, we're going to get the acidic form of the indicator, which is the first color. And then it is going to, of course, dissociate some. And when the hydronium ion comes off of the HIN, we get the IN minus, which is basically the conjugate base of the indicator. And that gives us our base form of the indicator, or our second color. Okay, so here is a big old chart that kind of gives us a little bit of information about indicators. So some indicators only have two color changes. Others will have an intermediate color that is between their quote-unquote in colors. If you can look at the pH of the color changes, indicators can help you differentiate between acids and bases. Okay. Also notice that all of these indicators transition colors at a different pH. And that all has to do with what the Ka of that particular indicator is. And that tells us when it will lose that particular H and become the conjugate base and change color. Indicators are often used in titrations to indicate the endpoint. So endpoint is slightly past equivalence, but because it's slightly past equivalence, it helps us be able to determine when we have neutralized our solution, and it can also help us determine what the dominant species in the solution is at that particular point. So analyzing the Ka and pKa as well as whatever the color of our solution is going to allow us to be able to tell a bunch of things about the particular solution, dominant species, the strength of it, etc. When you pick a titration for your, I said that backwards. When you pick an indicator for your titration, what you're looking for is a indicator that has a pKa value that is plus or minus 1 pH unit of equivalence. So we want something that transitions right there at equivalence, because then it'll tell us, hey, you've neutralized. All right, so this is an example of how we would choose the best indicator. So we are starting with a weak base, and we're titrating it with a strong acid. We're given the Kb for our weak base, and then we're given a bunch of pKa values for indicators. Okay, so I need to know the pH at equivalence, okay? And what I have here is I have a weak base, strong acid, so I know that my pH at equivalence is going to be acidic because, like I just said, I have a strong acid, weak base. So it's going to be an acidic salt. The only indicator that is even close to being near acidic is methyl red. If you were to solve for the pH of the salt, and the salt in this situation is NH4+, if you went through the whole process and found the pH of the salt, you would find that the pH of this particular salt is going to be 5.1. So indeed, it is methyl red. All right, so this is just a little bit of a visual. So we have two different titrations here. We have a strong acid and a strong base. We know that the pH equivalence is 7. So in this case, the transition for the indicator can be plus or minus whatever, the pKa of the indicator can be plus or minus 1 pH unit from our equivalence point. So methyl red definitely would work for us here. Thymol blue is a little bit more of a stretch because it is a little further than 1 point away, but in a pinch, it would be okay. Now over here, the other side, I have a weak acid and a strong base. So we know that's going to give us a basic salt, which you see with the equivalence being above 7. With it being that high, methyl red is definitely out of the question, cannot be used in this case. Thymol blue is the only one that you could even think about going with. All right, here's a chart that shows us a bunch of different indicators and their transition ranges, their low and their high pH colors. I show you this because I just wanted to make a small little note about, well, first off, you can definitely, there's a bunch of indicators to choose from, right? So that's one point I wanted to make for a bunch of different titration situations. The other thing I wanted to say was universal indicator is a common indicator. It goes through kind of the colors of the rainbow. That's not one particular indicator in there. It is actually a mixture of a bunch of different indicators that transition at different ranges, and that's why you get the rainbow effect. All right, so let's consider this generic equation for this following indicator. We are also given the pKa value of the indicator. So A wants to know what happens to the indicator equilibrium if an acid is added. So if we add H plus to the system, it's going to add a stress to the equilibrium. So the equilibrium is going to shift left, okay? It's going to make more of the bound acid. So it should shift towards the yellow color of the indicator. All right, now the converse is what happens if we put a base in there. Well, if we put a base in there, all the base is going to do is react with our acid. So essentially our acid is being removed from solution and it is producing the conjugate base and the H plus, okay? So this means the color is shifting more towards the blue region, okay? When pH is equal to pKa, we know that the concentration of our acid, which is yellow, is equivalent to the concentration of our conjugate base, which is blue. And if you have equal parts yellow and blue, then you get the color green. All right, now if this indicator was added to a solution who had a pH of 1.3, we want to know which form of the indicator is going to be the dominant species. Okay, so we're below our pKa of 4.9 at 1.3. So what that tells us is we are going to have a bunch of the bound indicator weak acid in our solution, so HIN. All right. Now let's look at these. These are structures of an indicator, both the protonated and deprotonated form, and we have to figure out which is which. So we sort of need to just analyze the structure. So here is where the structure differs, okay? So this one has the H on it, and this one does not, okay? So this one has the H. So this is the one that can donate the H. So this is definitely the acidic form, which means that this one, because it has an available spot to accept an H, is the basic form. If the pKa of the indicator is 9.4 and we put it in a solution that is 10.2, which structure is going to be more prominent? Well, hopefully you said the basic form of it. Number one, it's past the pKa of the indicator. Anything past it is going to be more basic. So hopefully that's exactly what you thought. So it's definitely going to be the basic form. Structure 2.